Okay, this is the exam 3 review, numbers, I think, 11 through 20. So number 11, two objects, and those objects are going to be called P and Q, moving through empty space with the same kinetic energy. So the kinetic energy of P is equal to the kinetic energy of Q. Object P has 6 times the mass of Q. So the mass of P is equal to 6 times the mass of Q. What's the ratio? We want to know VQ to VP. Okay, so working here, we would do 1/2 mass P, velocity P squared is equal to 1/2 mass Q, VQ squared. And what we need to do is we need to get this equation to look like that. So we need VQ over PQ equals something. And you're going to want to substitute that in. We need to substitute that so that the masses cancel. Because right now, these two don't cancel. So you substitute and solve, get it looking like that. And that's how you do that one. Which statement about the concept of work is defined by physics is false? So which one is not true? So just thinking about work. Work has 2 definitions. One, it's the force times distance times cosine of the angle between them. So if there's any amount of force, say if this is being displaced this way, if there's any amount of force in this general direction as the displacement, that's positive work. If it's perpendicular, that's 0 work. And if it's opposing or in the opposite direction, that's negative work. So let's go through. So no work is done by a force if the object moves perpendicular to the direction along with the force. So if it moves perpendicular, there's no work. That's true. No work is done by a force on an object that moves with constant velocity, where the velocity does not have a component along the direction of the force. So what that's saying is that basically if something has a velocity this way, that means that its displacement is also this way. And then it's saying that the force is perpendicular too, so that's the same thing, so that one's fine. No work is done by a force if the object on which the force is acting does not move. So if there's no displacement, then there's no work, so that one's fine. A given force acting on an object may or may not be doing work, and that's true. Because we could have an object sitting on the ground, there's the force of gravity, doing no work. Or if we remove it, it's going to fall, and now it is doing work. So that one, they're all true. Okay, now we got a crate, 36-pound crate is pushed along the floor by a horizontal force 1. And then you have force 2, force 3, and a friction force is shown. What kinds of work? So what it's saying is it positive, negative, or 0? So it's moving. Which way is it moving? Well, it says that there's friction, that F4 is friction. So this one right here, this is friction. Since friction is this way, the object has to be moving to the right. So now any force that's generally to the right would be positive. So looking at this one, that one's in the same direction, so that's positive. Friction is opposite, so that's negative. And then these two right here are perpendicular, so those are 0. What units of power? So power is change in energy over time. It's also force times velocity. It's also work over time. So if we just do some dimensional analysis, energy is joules, and that's seconds. Force is newtons, and velocity is meters per second. And work is joules seconds. So joules seconds is good, joules per second, yeah. Watts, that's what we call it, joules per second. We also call those watts, that's good. Kilowatt hour is not, because that is power times time. That's energy. So kilowatt hour is for energy. When a rattlesnake strikes, its head accelerates from rest. So here's the rattlesnake head. The initial velocity is 0 to a speed of 26 meters per second. So the final velocity, 26 meters per second, in a time of 0.44 seconds. Assume for simplicity that the only moving part of the snake is the head. And they give you a mass, but that's in grams. So let's go ahead and just convert that. That would be 0.150 kilograms. How much power does it need to accelerate in units of watts? So power is going to be your change in energy over time. And the energy in this case is going to be kinetic energy. So if we get the change in kinetic energy over time, that would be our power. It starts with 0 kinetic energy, and then it has some at the end. So all we care about is the final kinetic energy. So that's 1/2 mv final squared divided by the time. And from there we can just plug everything in. 2,988 kilogram car moves down a highway under the acceleration of 2 forces. One is 1140 forward, so we have force this way. Call it force 1, 1145. Expected on the drive while by the road. What? I don't know. On the drive while by the road. Whatever. The other is a resistive force. So resistive is going to be opposite. So that'd be force 2, 944. Find the speed of the car after it has moved a distance of 28 meters, assuming it starts from rest. So V naught is 0, and then it moves and has some final velocity, and that's what we want to know. So since we have 2 forces, what we want to know is the net work. The net work is equal to the change in kinetic energy. This one is doing positive work, this one is doing negative work. So we would have, remember work is force times distance. We have the distance, delta x is 28 meters. It's given in the problem. So we would have force 1 times delta x minus force 2 delta x equals the change in kinetic energy, which is just the final kinetic energy, and Vf squared. Plug stuff in and solve for final velocity. The 1677 kilogram car travels at a speed of 12.8 meters per second. What's the kinetic energy? Kinetic energy is 1/2 mv squared. So that's it. Stan does 179 joules of work, so the work is equal to 179 joules. While lifting himself up at distance, h equals 0.5 meters. What's his mass? So this is a change in gravitational potential. So the work is equal to the change in energy. So the work is equal to the change in energy is UG. So the work is equal to mgh. And we can just substitute and solve for mass. A plane designed for vertical takeoff, vertical means straight up, has a mass, so the mass equals 7.8 times 10 to the third kilograms. Find the net work, so we want to know what's the total work accelerating upward at 0.75, so they give us the acceleration. Acceleration is 0.75 meters per second squared through a distance of 29.5 meters. So that would be the height, starting from rest. So this one we're going to focus in. The net work is equal to the change in kinetic energy. Now it says that it starts from rest, so the initial kinetic energy is 0. So the net work is equal to the final kinetic energy, which would be 1/2 mv final squared. So we know the mass, we just got to figure out the final velocity. We know the acceleration and we know a distance. We don't know time though. So we would use the third kinematic. Vf squared is v naught squared plus 2a times delta x, or y minus y1. Just do delta x. So there's no initial velocity, so we just have that. So with that you can get the final velocity. The final velocity you can get the kinetic energy, which is the network. Two marbles, one twice as massive as the other. So we'll call them marble 1 and marble 2. So marble 1 is equal to twice the mass of marble 2. They're dropped from the same height. So 1, 2. When they strike the ground, how does the kinetic energy of the more massive compare to that of the other marble? Okay, well we know when they hit the ground, they're going to have the same speed. That's equal. The final velocity of 1 is equal to the final velocity of 2. But they have different masses. So there's a couple, I would focus in on each one. So kinetic energy of 1 would be 1/2 m1 v final squared, and the kinetic energy of 2 would be 1/2 m2 vf squared. So now they're going to have different kinetic energies, but they have the same velocities, and what you can do is use this and substitute that in there so that they have the same, and then maybe do a ratio or something. I don't know what the answer choices are, but that's how you approach it. Okay, that's the second set.